here in the very first question, I would consider this an easier question because the equation is given to us. However, in real life problems, the numbers aren't as nice as fake life problems. Okay? I don't know if that's a word or not, but here we have the depth of water. Tides come in and come out, come in and come out. Anything that repeats itself over a period of time will always make a sine or a cosine graph. So it's modeled by the following equation. Could you graph this using DAB-C? What's your d value? Okay, and when I'm thinking about this graph, I'm drawing my axes down here. Can you see that my d value, 13.7, I'm going to label 13.7 right there, dotted line. That's my center line. Then, d value, done. Amplitude. Amplitude is negative 4, well, the amplitude would be positive 4.5. So that means I would have to go up 4.5 and down 4.5. When doing this, do your best to create the right scale. If this is 13.7, 4.5 would be about there, approximately, and about 14.5. So up 4.5 would get me to 8.2, down 4.5 would get me to 9.2. And that's my maximum and my minimum. So my A part of DAB-C is done. We have a formula for the period. The period is always 2 pi divided by the B value, and the B value in this one is 0.16 pi. So your pi's will cancel out. 2 divided by 0.16, and that's 12.5. So that means on my x-axis, I can pick a random point, put 12.5, divide it into 4 equal sections. So this is 6.25, this is 3.125, this is 9.375. And since it's a real life problem, I should label what these things stand for. This is depth, and this is time. Okay. We're drawing a cosgraph, a negative cosgraph. A negative cosgraph starts at, check off B. It starts at a minimum, so minimum, then center line, then maximum, then center line, then minimum. And this is where we would normally draw a dotted line to say, this is what it looks like before the shift. And then you look at what kind of shift is there. But in this one, there is no shift. You see there's no adding or subtracting after that. So our final graph looks like this. And we curl the graph up nicely so it doesn't go below the minimum. Put arrowheads on. Perfect. There's our graph. So what I'm also going to show is that for those of you that have a graphing calculator, we can get this same graph on our graphing calculator. So what would that look like? Well, we make sure that we're in radians, so you can hit your mode button if you have a graphing calculator. Oh my goodness, my graphing calculator is fast. I'm in radians. Then we go to y equals, and clear out that equation. I'm going to write negative 4.5 cos 0.16 pi x bracket plus 13.7. And this will make this graph. However, when I push graph, I don't see it. Why? Because my calculator might just show me, in fact, I think most of you, if you do this, you're probably on the standard window. You might just see a little bit of it if you hit graph. Because your normal graph goes from minus 10 to 10, minus 10 to 10. Can you see if I only went up to 10, why I'd only see this little bit? Because this is 9.2. I need to see, I really want to see up to 12.5, and my maximum I want to see up to 18.2. So to see more on your graphing calculator, what you need to do is change the size of the window that you're looking at. Right now, I hit my window button. Right now, I'm looking from minus to 10 to 10 on my X, and minus 10 to 10 on my Y. So what do I want to look at? Maybe I want to look at minus 1, because I just want to see this a little bit, up to 13. Just a little bit past that. Maybe for my minimum, I want to still see minus 1 so I can see the x-axis. But I want to go up to 20 now, just to see if I can see enough. When I push graph, does this look more like what we drew? Yes. Okay. Now, for part B, it says that a ship, this is a fancy word for a big ship. Here, I'll translate this into easier English. A big ship needs at least 14.5 meters of water to dock safely. So if we go back to our graph and see what this would mean, you would need 14.5 meters of water. So it's only safe in this yellow section. So we need to know, and this is true for boats coming into areas with tides, they need to know when they can go in and when they can go out. Because if they screw that up, they're stuck. Their boat's like, uh-oh, we have to wait. And we have to wait for the water to come back. You just think, oh, hey, just wait a bit. No. Okay, so how could we do this with our calculator? With our calculator, you could type into Y2, you could type in that vertical line of 14.5. Now it draws that straight red line that we had from before. And your calculator is very powerful. It can find out where these lines intersect. So I can go second, calculate number 5, where they intersect, push enter, 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 and it says 3.48. The first one's right here. Maybe here, 3.48. If you want to find where the other intersection is, you just have to do it again. Second, calculate, go down to number 5, intersect. But it'll always find the closest one, so I'm going to use the arrow key. Until I'm closer to the other one. And then I push enter 3 times. And it would find the other. So technology helps you find this. How would you do it otherwise? You would have to take your equation and you would have to plug in the 14.5 for the y. And then you'd have to solve this using your algebra skills. Still be allowed to use your calculator, but that's a little bit harder. Okay? When you get to university, you'd be expected to be able to do that, but you won't get any ones without a calculator to solve that. Like, I won't even ask you the graphing calculator, just showing you that it could be done. What we're going to get more often is questions like, oh yeah, skip that. Questions like this. This is a more typical question that you're going to have as a word problem. And what makes it more typical is that the equation isn't given and you have to find the equation. So first of all, you have to read the question and be able to draw a graph of what's going on. Okay? So Ferris wheel, that's one of those fun things that looks like this. Oh. Move it down a bit. There we go. Of course, it would have spokes connecting it. Right, there we go. Oh, and you have like fun little chairs. As you're going around, you're enjoying your life. This is you, you're so happy. There we go. Enjoying the Ferris wheel. So this is the picture of the item that we have. What's happening? It tells us the Ferris wheel has a radius of 15 meters and rotates once every 20 seconds. Passengers start at the bottom. It'd be much scarier if they said you have to get on the Ferris wheel at the top. Okay, so it's typical that Ferris wheels start at the bottom. So I drew the picture over here so that simultaneously over here, I could draw the situation. You're getting on at 1 meter above the ground. So I'm going to say this is 1 meter right here, 1 meter. This is where you get on. If it rotates every 20 seconds, can you see that at 20 seconds, you would be back at 1 meter above the ground? Now what happens in the middle? Okay? Where would you be at 10 seconds? Oh, we're gonna sorry, captivate you for a second. No. Take this one back. There we are. Oh. So you're starting, here you are, at 0 seconds. 20 seconds, you would have gone and got back to where you started. Where would you be at 10 seconds? Right up there at the top. And so at 10 seconds, you're at the top. What value is this? How would you figure out how high that is? 15 times 2, because the radius is 15, so you'd be 30. Should I write 30 here? Or should I write 30 plus 1? 31. And where would you be at 5 seconds? And where would you be at 15 seconds? You would be right here with the center line, your sinusoidal axis, which will be at 16 because it's up 15, up 15. So now we can put a point up here at maximum. At 5 it's at 16, at 15 it's at 16. And look at that. Makes a perfect sine or cosine graph. And if you can draw the graph, you can un-dab-C it to get your equation. The D stands for your center line. Can you see easily from your graph now that that's at 16? Your A helped you find your maximum and minimum, but we have the maximum and minimum. Your A value is from the center line to that maximum. That's going to be 15. Your B value helps you find your period, but we know that our period is 20 seconds. So how would you take the period and find your B value? So just like there's a formula that says period is equal to 2 pi over your B value, you could rearrange that formula so that your B value is 2 pi over your period. If your period is 20, then your b value would be 2 pi over 20, which could reduce to pi over 10, but I actually like 2 pi over 20 better than pi over 10, because if it's written 2 pi over 20, then you can see the period is 20 right in the equation. And the c value changes. So in this question, it says, find its equation. Well, it could be a sine graph or it could be a cos graph. So we're going to find a couple of them. Whether it's a sine or a cos graph, the a value is 15. If it's a sine graph, the b value is still 2 pi over 20, and the d value is 60. What's going to change is where the starting point is. Where does a sine graph normally start? On the center line, going up. Where do we have on the center line going up here? Right there. And I'll do it in purple. Can you see that that is a shift of 5 to the right? So I would write in purple minus 5. Let's say I wanted to do a cos graph. Y equals, the amplitude is still 15. The period is the same, so the b value is still 2 pi over 20. The d value is still 16. But where does a cos graph start? At a maximum. Can we find a maximum? I'm going to do this in black. Here's the maximum. When is that? With a shift of 10 to the right. And do you know what the favorite equation is for this one? Like these, you could pick more. Can you see? Oh, I could do another sine graph taking a different starting point. But the favorite equation for this one would probably be this. You tell me why this is the favorite. Can you see a negative cos graph is really nice because it's already starting at a minimum, and then you don't have to worry about any shift. So that's probably a favorite, is a negative cos graph in this case. But what the kind of questions you're going to get with your word problems are more likely like this. They tell you the situation and say, can you find the equation? So you have to be able to work through the situation and think of the graph and draw the graph. Once you have that graph, you know the center line, you know the amplitude, you know the period, so you can find the b value. Then you have some choice. Depending on which starting point you use, you'll have different shifts. So if I use a cos graph, it starts at a maximum, it shifted 10 to the right. So I had to do a minus 10. Is this Ferris wheel exciting, or is it just normal? A 15 meter radius. Is that pretty big? That's decent. I mean, we could have made this question a lot more exciting. You know how big that Ferris wheel would be then? With a 15-kilometer radius? Or yeah. And then you go around in 20 seconds? I think you would be dead. Yeah. I think physically, if we could figure out with 15 kilometers what the actual circumference is and find out how far you travel, if someone's doing it, what is the circumference? 2 times pi times r, like 90 kilometers, 94 kilometers in 20 seconds, right? That would mean if you're 94 kilometers in 20 seconds, times that by 3, you would be going 282 kilometers in a minute. Times that by 60, and you would be going 16,920 kilometers per hour.
I
I think you might be dead.
Maybe.
Right? You would be like, here's you. You'd be like whipping around here, and I think like you get such force that I think at this time this would be like possibly. I don't know if that would be. Your seatbelt that you'd be then ripped where the seatbelt is probably. Wait. I think you would be if you were going backwards. That fast. No, that would. If you're going forwards, you'd be okay. You'd be pressed against the seat. So you'd be pressed against the seat pretty good until you got to the top. Ooh. It's. Yeah. All right. So with that image, we'll stop for the day. Yes, I can slide it down.